Hi Professor, my name is Nitinsai Karuturi. This is my final presentation for the project. My project is recognizing vehicles in radar surveillance images, and I achieved a final accuracy of 99.5%. Coming to the presentation's agenda, this presentation covers 4 sections: final pipeline architecture, hyperparameter optimization, image analysis evaluation, and final results. Here, my complete pipeline has 6 steps. First is data loading from MSTAR dataset, which contains 696 training chips and 822 test chips across 3 vehicle classes, which are BMP2, BTR70, and T72. Step 2 is Lee adaptive filtering to remove the multiplicative radar speckle noise. Step 3 is CFIR segmentation to isolate the vehicle target from background clutter. And step 4 is morphological cleanup to remove any stray noise pixels. Step 5 is a standardized 64 by 64 center crop. And final step is the SARnet CNN. 3 convolution blocks with batch normalization, followed by 2 fully connected layers trained with the best configuration of LR 0.0001, batch size 16, and dropout 0.3. Coming to hyperparameter optimization, I ran a full grid search across tool configurations, 3 learning rates, 2 batch sizes, 2 dropout values with 10 epochs per configuration. Here, learning rate had the biggest impact. Learning rate 0.01 performed poorly at 75 to 87%. LR 0.001 improved to up to 97.8%. But LR 0.001 produced the best results. The best configuration was LR 0.001, batch 16, dropout 0.3, achieving almost about 98.4% during the search. The key finding is that a lower learning rate with small batch size gives the best stable configurations on the small dataset of 232 samples per class. This slide answers whether pre-processing actually helped. On the left you can see a real MSTAR chip before and after the leaf filter. The raw chip has visible speckle noise in the background, but after filtering the background is much cleaner while the vehicle return is preserved. The numbers prove the impact here. HOG plus SVM with pre-processing achieved 91.4%. CNN on raw chips without pre-processing achieved 94.9%. And CNN with full pipeline and tuning achieved 99.5%. The pre-processing pipeline alone contributed a 4.6% improvement over the same CNN architecture on raw chips. Here, the full comparison table shows HOG plus SVM at 91.4%, CNN without pipeline at 94.9%, and CNN with full pipeline and tuning at 99.5%, an 8.1% improvement over the baseline. For per class scores, the tuned CNN achieved FN of 0.99 for BMP2, 1 for BTR70, and 1.00 for T72. The BMP2 to BTR70 confusion, which has 60 misclassifications in the baseline, dropped to just 2 in the final model. The confusion matrices confirms this improvement across all 3 models. HOG plus SVM shows 22% BMP2 to BTR70 confusion. CNN without pipeline reduces this to 8%. The final tuned CNN brings it down to just 1%, nearly eliminating the dominant error pattern completely. T72 achieves 100% correct classification in all 3 models. This slide shows 3 real MSTAR chips, 1 from each class, processed end-to-end through the full pipeline and classified by the tuned SARnet CNN. All 3 are correctly identified with confidence scores above 98%. And coming to the conclusion, to summarize, the pre-processing pipeline contributed 4.6% improvement over raw CNN. Hyperparameter tuning found LR 0.001, batch 16, dropout 0.3 as optimal. Final accuracy is 99.5%, 8.1% above the baseline, with BMP2 to BTR70 confusion reduced from 60 to just 2. So, thank you, Professor. If you have any doubts or feedback to give me, please contact me.